So the ALEKS questions about elemental analysis are basically asking you if you can calculate empirical formula. So remember, empirical formula is the smallest whole number ratio of elements in a compound. For an ionic compound, the empirical formula is always the same as the formula unit, because remember, ionic compounds, they just have like infinite arrays of anions and cations all packed together. So we just give the empirical formula as the formula unit, which is the smallest repeating unit. It's the same thing, okay? When you have something that is molecular, so exists as discrete molecules, covalently bonded, okay? Sometimes the empirical formula is not the same as the molecular formula, because the molecular formula describes the entire compound, one entire molecule of the compound. So the molecular formula is the composition of the entire molecule. So 9 times out of 10, if people get confused on these kind of questions, it's differentiating between what empirical formula is versus what molecular formula is. Now, we can get to the empirical formula by using that concept of mass percentage. Okay, it's basically sort of looking back the other way, because if you have mass percentage, that is relating the percent by mass of each element you have in a compound, and it should add up to 100%. So if you have 100 grams of the compound, those mass percentages, you can just say, hey, that's a mass in grams. We know how to convert mass in grams to number of moles. So if it's a binary compound and has 2 things, or if it's ternary and has 3 different elements, even if it's got 4 or 5 different elements, you can take mass percentages, change them into mass in grams, and then use the molar mass of each of those elements to get the number of moles of each of those elements, okay? If you got the number of moles of each of those elements, you can take that and work out the smallest whole number ratio. Okay, sometimes it takes a little mathematical trick to get you there, but let's just work through a problem and see how we do. So here we've got 18.1% carbon, 2.27% hydrogen, 79.8% chlorine. So we're going to say that we have 18.1 grams of carbon, 2.27 grams of hydrogen, and 79.8 grams of chlorine. Okay, so what we're going to want to do then is convert the mass in grams to the number of moles. So let's do that for carbon first. If we've got 18.1 grams, the molar mass of carbon is 12.011 grams for every 1 mole of carbon. So we're going to just have a number of moles of carbon. So quick as you like, 18.1 divided by 12.011 gives me 1.50695 moles of carbon. Now, you don't have to go to a super big number of sig figs on this, just enough so that eventually we'll be able to get the nearest whole number ratio, okay? So we're going to do the same for the hydrogen. So if we have 2.27 grams of hydrogen, we know that 1 mole of hydrogen weighs 1.008 grams for every 1 mole of hydrogen, okay? So 2.27 grams divided by 1.008 gives me 2.251984 moles of hydrogen. Again, I've not given all the decimal places because we're not going to need them, okay? And then finally for chlorine, we have 79.8 grams, okay? And the molar mass of chlorine is 35.453, I think. Yeah, that came off the top of my head. For every 1 mole of chlorine. So that is going to be 79.8 divided by 35.453 gives me 2.250867 moles of chlorine. Okay, so when you get the number of moles of each element that you have, sometimes it can be a little bit, oh, what do I do next? Because you get these like long non-integer numbers, and it's like, what do I do with this now? So my simple trick is to then divide through by whatever the smallest number of moles is to each of these, because you're going to then force one of these to be your 1 in your ratio. So in this case, it's going to be the moles of carbon, right? Hopefully we can all agree that 1.5 is less than 2.25. So if we just divide these all through by the 1.50695 moles, okay, to get a unitless what do you call it? A unitless ratio, which hopefully is whole numbers. Or if it's not, we can make it whole numbers. Okay, so that's going to be 1, 2.25 divided by 1.5. If you need to, use your calculator, that's okay. But at this point, we're not really worrying about more than about 0.1 in terms of sig figs and stuff, right? So that gives me 1.5. Like, one decimal place is cool at this point, is what I'm saying, especially if you're doing this in a lab for like an actual practical experiment. Like, it's not going to be that accurate, okay? So this is our ratio. As you can see, it's not a whole number ratio. Our definition of the empirical formula is the smallest whole number ratio of elements in a compound. So at this point, you may need to multiply, okay, by an integer just to tidy that up and get whole numbers. And remember, if you have to multiply through by an integer, you've got to do it to all of them. So if your ratio, you have like a 0.25, you're going to multiply them all by 4, right, to get rid of that 0.25, okay? If you have like 0.33 or something, you're going to multiply all by 3 because it's a third, right? And in this case, we've got a 0.5 in there. Actually, we've got a few 0.5s, which means we're going to have to multiply through by 2. So those are like the common options that might come up when you don't have a exact whole number ratio. So if I multiply by 2, what are we going to end up with? Well, 1 times 2 is 2. 1.5 times 2 is 3. 1.5 times 2 is 3. So I've got a ratio of 2 carbons to 3 hydrogens to 3 chlorine. So I could write that like a chemist. So that'd be C2H3Cl3, and I'm going to just try and write that as a subscript. C2. No, that's the wrong thing. Let's not do that. Let's not do that. Should be a subscript. C2H2 Cl. No. H3. Oh, it's so hard to draw. Cl3, just to make sure you're getting that as subscript. So that's coming from this ratio right here. Okay, I think we should do another one, just because the more of these you do, the better it is, really. So let's see what else we get. All right, carbon, hydrogen, oxygen. Why not? Okay, so again, what you're going to do is you're going to take the mass percent of each of these and say, hey, if I have 100 grams of this, then I got 63.1 grams of carbon. And I know the molar mass of carbon is 1 mole of carbon is 12.011 grams. So that is going to give me how many moles of carbon in this 100 gram sample? It's going to be 5.2535 moles of carbon. All right, so let's do the same for our hydrogen and oxygen. So hydrogen, we have 5.29 grams. And the molar mass of hydrogen, 1 mole of hydrogen weighs exactly 1.008 grams. Okay, so 5.29 divided by 1.008 gives me 5.25. Would help if I found the decimal point. 5.2528577 moles of hydrogen. Okay, so you can see, right, in terms of rounding and stuff, please don't give me an empirical formula that's like carbon 19 to hydrogen 20 or something like that. Like, it's going to be 1-to-1, okay? It's close enough. So oxygen, 31.5 grams. Every 1 mole of oxygen weighs 15.999 grams. Whoop, where did you go? So 31.5 divided by 15.999 gives me 1.96887 moles of oxygen. One of these is not like the other. So sometimes if you got like 5.25 for all 3 of these, you could save a bit of time and be like, it's 1-to-1. Okay. But in this case, we're like, okay, we're going to have to relate them all to the smallest number of moles, which is our moles of oxygen, right? 1.96887. So we're going to divide each of these guys through by that amount to get our smallest whole number ratio. One of these is going to turn out to be equal to 1, which is going to be this one, forcing it to be 1. Okay, so then what are all the others relative to that? 5.25 divided by 1.96887 is going to be 2 points. Oh, I'm so glad I did this. 2.666. Okay, and I think this one's going to turn out pretty similar, right? 5.2535 divided by 1.96887. This is a nice tricky example to spot, right? 668. Okay, hopefully you guys can see this is 2 2/3. Okay, so how am I going to get 2/3 to be like a whole number? I'm going to have to multiply it by 3, right? Because if I multiply 2.668 times 3, that's going to give me 8, okay? So, because it's a 2/3, well, truly the same as it's 1/3, right? So, I'm going to multiply all y'all by 3. Lovely stuff. All right, so 2.668 times 3 is going to be 8. Would help if I press the right button. 8 to 3. That is a real nice, tricky empirical formula. So that is going to be C8H8O3. Ooh, such a tricky one. Love it. So then you'd write that as a subscript C8H8. Wow, that's super skillful, Erin. O3. All right, there you go. Have fun with that.